We're good. Creative solutions. It's more important today because we have at least 2 people gone, if not 3, which is what I was working toward to get solutions. So today we should be able to finish calculate the velocity of a point on a rigid body based on the relative velocity. So last time, what did we do last time? We found the position and then derivative to get velocity acceleration. Now we're going to use relative velocity. And then beyond this, so there's actually 2 different ways we can use relative velocity. One is the instant centers and one is this. And then beyond that, then we'll go to relative acceleration, which is more complicated because we have the normal and tangential. Here, what's a good point to use as a reference point? And then use these relative velocities to calculate linkages. Questions on the homework? Yes?
I just want to see how to set up. This is theta prime. Yeah. Right? And so you can use the law of cosines to relate the 3 sides. Or you can set up the height and then take the derivative. As an example, does it look like that? Yeah. Then all the derivatives will be taken for you.
Yeah, but also
not that hard.
it's unraveling.
That would be the 2 ways. One way is to set up an intermediate height, and then the calculus is easier. Or you can use the law of cosines, figure out what theta prime is, and the omega of this is the same as the omega of that. All right, so now we have relative velocity VB with, oops, wrong way. This is the button. Press VB with respect to A, or in VB. What does VB with respect to A mean? Or what is VB with respect to A is what? This is a discussion question. All right. What? We are VB. Does always? It's all of the above. So we're talking rigid body motion. Now the question. Here we have a yo-yo. Oops. Yo-yo's facing. Okay. String is coming off the bottom of the yo-yo. Right? We put it on the thing. Now if I pull on this at 2 inches per second, which way is it going to move? Is it going to move to the right or to the left? Or it won't move or up? No! Because this is a presupposition quiz, and so if you see what happens, then you're no longer presupposing what happens. Well, I'll pull it later on in the class. So now you can vote. It's going to move to the left, to the right, it won't move, or up. The string is coming off the bottom. All right, 5, 4, 3, 2, that might be everybody actually. And there's our, so most people say it's going to move to the left, 2 people say the right, 1 person, 5 people say it won't move. All right, we don't know what the right answer is yet, so we'll just leave it at that. I know. It's what your presupposition is. And so your presupposition is your presupposition that's correct. It's whether you get it correct or not. I'm not going to penalize you if you get it wrong. So, when we have this situation here where we have a flywheel rotating, which link is going to general plane motion? AB or BC? General plane motion. AB. BC is going through rotation. We talked about that last time. AB is general plane motion. Slider block is going horizontal, and so this link is both rotating and translating. We know direction of BA, right? It's going to be horizontal. We know the direction of BB, right? BB is R omega, and it's always perpendicular to R. So it's either going to be going to the up and to the left or down and to the right, but it's always going to be perpendicular. So basically we can use the relative velocity between B and A to figure out what omega of the connecting rod is going to be found. Here we have a planetary gear set. So planetary gear sets used in automatic transmissions. Here we have one made by one of the students last year. What do we have? We have we have an arm. We have gears on the arm. The gears on the arm are called the suns. Now the planets, the gear in the middle is called the sun, and then the outside is called the ring gear, because it's like a ring. Now if we can everything back in again. So what do we have here? We can have an omega of the arm. And we can, so basically the center can turn and the arm can turn independently, or you can hold the arm fixed, turn the center and then the ring. So basically you can hold the ring fixed and then get an omega of the arm, or you can hold the arm fixed and get the omega of the ring. So the gears are still engaged, but by different clutches you can get different speeds. So by locking different gears you can get different gear ratios for your system. I can pass that around. At the end of class, we're going to actually look at how to calculate numbers, but we can use relative velocities. Basically, what we have is the velocities at the point in common are going to be the same. The velocity here is going to be the same as well. So we know the velocity here is r omega, velocity here is r omega, velocity here. So it's a bunch of r omega relative velocities. So basically, what do we have? We have general plane motion. Here's my kidney. So we have AB. So we want to basically general plane motion or translating and rotation. How can we describe this? Well, we can combine it as a combination of translation, where we start here. Anyway, we start here. We first translate. Let's do it here. So we first translate, and then we keep A fixed and then rotate about A. So the motion can be described as everybody translating together, where everybody has the same velocity, and then we rotate about point A. That's the combination. Or we can translate and we can rotate about point B. What do we know? Between A and B, how can we have a relative velocity? If we're rotating, right? We're not going to have the r dot component because r is not changing. The length is not changing, but we can have the r theta dot component of your polar coordinates, which is r omega. And so basically what we're going to be doing is the change in B is equal to the change in A, translation, plus the change in B with respect to A. And this is going to be r times theta. And so when we take the derivative, we get the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. And that velocity is r omega. So we have the displacement in B, and that's due to translation rotation. We can basically break it down into translation and rotational component. And those are indicated in green. So, take the derivative, you get the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. And basically this derivative is omega cross R, or it's r omega if r is the perpendicular distance from the angle of rotation. Omega has a k component, it's out of the board. So hopefully you don't get hit by these omegas. We have a birthday kid downstairs if you get hit by an omega. So it only has a k component, so it's always perpendicular to the plane of the board. So what do we have here? Here we have a piston, and the piston is off at an angle. Basically what we know the velocity of A. What do we know about the velocity at A? It's moving left and right. We know the direction. We may or may not know the velocity, the actual velocity. What about the velocity of B? Well, we know since B is on length BC, we know the velocity of B is going to be perpendicular to this length. So we know the direction of B. If we know omega BC, then we actually know the velocity at B. What do we know about the velocity of B with respect to A? That says if you hold, or A with respect to B, if you hold B fixed, what direction is the velocity of A going to be? It's going to be perpendicular, so it's going to be going up and down. So the velocity of B with respect, or A with respect to B is if you hold it, or A with respect to B, let's go to that. If you hold A fixed, what direction is B going to move? It's going to be moving up and down. That's the relative velocity. You ignore the rest of the world. When you're calculating the rest of the relative velocity, you ignore the rest of the world. And so you combine everything, and so basically we can use these to figure out what's going on in linkages. We know velocities, so we know the velocity of B is perpendicular to here, the velocity of A is going to be going here, and then we can basically go, the velocity of B with respect to A is also going to be vertical. So we can basically have a vector equation, which is a triangle, and then based on the triangle you can figure things out. Special cases, when the round thing rolls, the wheel rolls, and we're not slipping, where do we know the velocity? The velocity at the ground is 0 if we're not slipping. Then the velocity of the center is going to be what? R omega, because the velocity of A is 0, so the velocity of the center is just going to be omega R times omega. So typically you're going to have a wheel, the velocity of the wheel is R omega. And so the BB, no direction, it's going to be horizontal, and it's going to be moving like that. Relative velocity, either a Cartesian or scalar components. So basically we want to set up an XY equation. We have velocity in the X, velocity in the Y, and then basically get our components. That gives us two equations, two unknowns. Or we could have a triangle. Whenever you have a triangle, you can use, how do you get the sides of a triangle? Law of cosine. That would be your other method of getting different things. And then basically, typically we use scalar equations, X and Y. We want to line our X and Y along an axis that we, basically you want to line your X, Y along one of your knowns, or your unknowns, and then you get a nice equation. Vector equation, draw the vectors, assume a direction, and then Cartesian, basically breaking the X, Y components. And then what happens if you get a negative answer for omega? It's going the opposite direction you assume. That means don't stress out on which way you think it's going to go. Don't try to solve the problem in the head. Just assume always omega is, right-hand rule is omega is what? Counterclockwise. Assume omega is counterclockwise, and if you get a negative number, then it means you're a bad person. So it means that it's just rotated in the opposite directions. But don't stress out. So, example 1. What do we have going on here? We have A and B, and basically we know A is moving to the right at 3 meters per second. So basically what do we want to find out? How fast is B going to be going? How can we do it? Last class, how could we do it? Well, you need a relationship between this length here and this length here. What's that? This side squared plus this side squared equals 1.5. Take the derivative. That's how we would do it last class. Now we're going to use relative velocity. So, what is our equation? VB equals VA plus VB with respect to A. Very good. Now if we draw our beautiful picture, right, so here is A, here is B, and then what else we need? So basically what do we have? The other unknown is, right, how fast we're rotating. So again, we're doing BB with respect to A, which means just looking at this, where are we rotating about? B with respect to A says we're rotating about A. So always put your omega about A. We're assuming we're rotating about A using a relative velocity, so this would be omega AB. Okay, what direction is VA? Well, that's known. It's to the right. This is VA, and that's given to be 3 meters per second. What direction is VB? VB we know is going to be down. So we know that VB is going to be going down. VA is going to the right at 3 meters per second. What about VB with respect to A? Relative velocity, magnitude is r omega. Relative velocity is always r omega. What direction? Perpendicular to the radius. Right, so if we're rotating down like this, basically what we're going to get is going to be perpendicular. Let's make it a different color, since I have colors. So this is B with respect to A, and it's going to be perpendicular to, this is RB with respect to A. Right, so the relative velocity is always perpendicular to the radius. How do we figure out which way to draw the arrow? Well, if you draw your omega about A and you cross your vector, then the arrow here points in the same direction as the arrow here. So as it's rotating around, it's always going to be pointing. So this arrow is always pointing in the same direction as this. And so BB with respect to A is going to be going down and to the right and has magnitude of what? R omega, so it's 1.5 meters times omega AB. So far, so good. Here we have a beautiful vector equation. Now, what direction? Now we need to set up an xy axis. How do we want to set up xy? Yeah, we could do that. We could just do x, y. It's actually easier if you set up this x, y. The math are easier, but assuming we want to know both information, if we wanted to know omega AB and BB, then we can go that. So basically, this is our equation. So in the x direction,
which x, y are we using?
we're using this x, y. Because I can't think that hard this morning. So this would be actually an easier one, but my brain is not working that good. So what's our equation in the x direction? What's this? 0 equals 3 meters per second times what? Let's see, this is 30. And then, no, BB with respect to A is not.
Minus cosine 30. Minus
What?
sine 30.
So BB, this is BB. BA is 3 meters per second. Positives to the right.
Minus 3.
So minus
1.5 times omega.
1 point omega.
1.5.
1.5 omega, no, meters times omega AB times, because this is pointing to the left. So this is 30, if this is 30, then this is 60, which means this is 30, which means this is 60. So let's do sine 30.
Yeah.
Which is a half. right? So that's one equation. From here we get that omega AB is equal to 3 meters per second divided by 1.5 meters times sine 30 is a half. And so this is equal to 4 radians per second, hopefully. Okay, and then our other equation is in the y direction. Positive is going up. What do we get?
Minus B.
It's minus VB. We assumed it was going down. Is equal to VA 0 plus VB with respect to A is minus 1.5 meters times omega AB is 4 radians per second times cosine 30 degrees. So, negative cancels with a negative, which means what? We have a positive number, which means we assume correctly that this is going to be going down. So we get VB is equal to 5.2? Yes. Meters per second, and that's going to be down. So basically you end up with a vector equation which you can solve going down. All right, so that's the first example 1. Example 2, a little more complicated. Now we have 2 links. We have that, we have that. This is 30 degrees. This is going vertical. Okay, so there's our beautiful thing. We're given that this is 12 radians per second. This is 0.3 meters. And this is 0.6 meters, and that's 30 degrees. So we know how fast OA is rotating. We want to find the velocity of B and the angular velocity of rod AB. So we probably should label our points. This is point A, and this is point B. Okay, what's our equation? VB is equal to VA plus VB with respect to A. There we go. VB equals VA plus VB with respect to A. And these are vector equations, which means they're going to have a magnitude and direction. What do we know about VA? It's R omega. VA, point A is on link OA. This was point O. And so therefore, the velocity of A is equal to the velocity of O, which is velocity of O? 0. It's not moving. It's the ground. So the velocity of A is equal to the velocity of O, which is 0, plus the velocity of A with respect to O. What's the velocity of A with respect to O? R omega. Whenever you have a relative velocity, it's R omega. And so it's going to be going, and it's perpendicular to R. And so arrow matches arrow. So this is the velocity of A, which is equal to what? 0.3 meters times 12 radians per second. So that's your velocity of A. What about the velocity of B? What do we know about the velocity of B? It's either going to be up or down. What do we want to assume? Up. Okay. So we know the velocity of B is up because it's in this beautiful slide thingy. vertical channel. So that's that. What's the velocity of B with respect to A? It's r omega. So, and we're rotating about what? We're assuming we're rotating about A, so let's write our omega. This is omega AB. And we're assuming counterclockwise. Why? That's a right-hand rule. Positive would be out of the board. Okay, so what's the velocity of B with respect to A? It's going to be perpendicular to AB, and it's going to be up. So this is B with respect to A. It's going to be perpendicular to RB with respect to A. So, BA is to the left, BB is up, BB with respect to A is up and to the right. Now, what do we have? This is 30. So this is 60. So this is 30. So this is 60. Because you always naturally want to draw things at 45 degrees. It just makes you feel good. So it's better to exaggerate your angles so then you never get confused on which is 30 and which is 60 and which is 30. That is, if we would draw it like this, 30 is acute or obtuse? Acute. So if we would draw it really like this, right? This is BB, and this is perpendicular, BB with respect to A. Any question about what's 30 degrees? Now if you exaggerate it, actually this is about 30 degrees, then this is, right, so if you exaggerate your angles, then you're never going to get confused on which is 30 and which is 60. Oh, 45 looks so beautiful. But then you get confused on which is 30 and which is 60, so then you can sometimes get confused on your sines and cosines. All right, so now we go back to our vector equation. What do we know? BB, what do we know about BB? BB is going to, we assumed it's going up. So BB we know is up. That's equal to, what's BA? BA is equal to 0.3 meters times 12 meters per second, and that's going to be going to the left, plus BB with respect to A. That's a magnitude of what? R omega, and so R is 0.6 meters times omega AB, which is our other unknown in our equation. And that's going to be going up and to the left at an angle of 30 degrees. So far, so good? So, what do we do now? Assume a coordinate. So, we'll assume x, y, just to make life easy. We're aligning it with one of our unknowns, BB, and we like up and down rather than sort of off at an angle. And so, in the x direction, which is perpendicular to one of our unknowns, we get 0 equals what? Negative 3.6. This was radians per second, not meters per second, because our units are meters. So this would be 3.6 meters per second plus 0.6 meters, oops, I've changed colors, times omega AB times what? Sine 30, which is a half. And so based on this, we can get that omega, sorry, omega's green, omega AB equals, and this is positive, so it's equal to 3.6 divided by 0.6, and then a half. And that's equal to what? 12 radians per second. So, okay, so that's that. And then in the y direction, what do we get? BB equals 0 because this is horizontal, plus 0.6 meters times 12 radians per second times cosine 30 degrees, which means we can get BB equals 6.24 meters per second. Yeah.
Is it just a coincidence that our omega is the same about A? As it
Yes.
is about
At this instant, the omega is the same. What's going to happen in the future? This is going to be moving up. This will be at an angle. And yeah, it's just at this instant. Next class, we'll be able to look at this and say it's going to have the same omega. This class is magic. Next class, we can do it in our head. So, something to look forward for next time. We can do this problem in our head, at least omega AB. So again, we use relative velocity. BB is equal to BA plus omega AB cross RB with respect to A, which is R omega perpendicular to R. All right, let's do an easier problem. Disk is moving with a velocity at point O of 15 inches per second, and omega is 2 radians per second. Determine the velocity of point A on the disk. With respect to the ground.
Oh, yeah,
'Respect to what?
The ground. All right, we'll stop at a minute 30. We have 20 seconds. More seconds? Is that everybody? Okay, everybody. I guess it's everybody. Oh. Okay, is it possible for the velocity of A not to be 0?
Yes.
Yes.
If we're sliding, right? So we take our yo-yo and we throw it with an initial velocity like this without rotating. Initially it's sliding, and then it ends up rolling. That becomes that's too far. We could figure out how fast it's going to be rolling later on. So the answer is not A. The answer is not A.
Good.
Let's use our relative velocity. We know. So what would our equation be? BA equals BO plus BA with respect to O. Oh no! We don't have any B's in our equation. What are we going to do? Hopefully we can figure this out. Let's try again. The answer is not A. right. We have about 10 more seconds. So 2:05. 5, 4, 3, 2,
Oh, wait.
0. Oh, there's 20 people now. All right. So velocity of O is 15 to the right. Velocity of A with respect to O is what?
R omega?
It's R omega. R is 2. Omega is
2.
that's 4. Which direction is it?
Negative. Left.
But remember, you got to put your omega around O down here. So omega is to the left. The velocity of A with respect to O will be to the left, so it's 15 minus 4, which is 11. Which was B. All right. Yeah.
Why is it not 0 again? I'm sorry.
It's slipping. So if we're rolling without slipping, then the velocity is equal to R omega.
How do you know it's slipping?
Because we know omega and we know V, and V is not equal to R omega. So there's two cases. If we're slipping, then V is equal. If we're slipping, then we know omega and we know V, and they're independent. If we're not slipping, then V is equal to R omega. So if we're slipping, we know the force here is what? No?
Or no,
Mu n. Right? If we're slipping. If we're not slipping, we don't know what the force is, but we know that V is equal to R omega. That's next chapter. All right, here's our yo-yo. We know the velocity of the string is 2 inches per second. What's the velocity of the center going to be? Relative velocity. Where do we know the velocity? We know that this is 2. Where else do we know the velocity? Now we're rolling without slipping, so velocity of A is 0. Use that information to figure out what the velocity of the center is going to be. No. Now we know the velocity of A is 0. We are not slipping. It's a different omega.
Oh, it's a different one.
It's a different omega, a different problem. Before we said the velocity of A was not equal to 0, it was 11. Now the velocity of A is equal to 0. We know the velocity of the string is 2 inches per second. What's the velocity of the center going to be? Going back to our initial yo-yo problem. Coincidentally, no. All right. How about 2:30 stopping? So 15 more seconds.
This is exciting and you forget to answer the questions.
Yes.
3, 2, 1, 0. Uh-oh. No, we don't have to. All right, what's omega? 2. Which direction? The way it's drawn. So what's the velocity here? You have to draw omega down here. R is equal to 2. Omega is equal to 2. So it's 4. Which direction? Omega is drawn this way, so omega has to be drawn this way so that it's in this direction.
What?
Why do you use it?
Right? So we figured out, right, that this is 2 radians per second. This is 0, right? That was the first equation. We know that this is 2 meters per second, right? So what's the velocity at the center going to be? Right, everything is red. This is crazy. We have 4 red pens. What's the velocity going to be at the center? R. So R is now equal to 2. What's omega? Omega is 2. What direction are we going to go? Well, as long as no, you've got to follow this arrow. This arrow tells you which way you're going. We're going to be going this way.
If you're going that way, the velocity isn't going to be 2.
What?
Your velocity at that of the string or whatever you're pulling. I don't get that. In a sense.
All right, here we have it. String is at the bottom.
What if you're pulling it open?
What are you pulling it open?
Like on top.
Start with this.
You put it at the top. Whoop.
I still don't understand why we put these velocity going this way for this one, but the previous one we had velocity going that way.
Because it's the velocity, this is the velocity of A with respect to O, and so we're rotating about O. Here it's the velocity of O with respect to A, so now we're rotating about A. This is the point with 0 velocity. This is the point where we know the velocity. And so, or you could do it the other way. I mean, you could also do it where this is now 1. This distance is 1. And we're rotating about A, where we know VA is 2 inches per second. So and we're still rotating about A, so this is 2 radians per second. So what about the velocity of O now? It's equal to 2 inches per second plus 1 times 2 radians per second, which is still equal to 4 meters per second. Yeah.
If you started with a yo-yo at rest though, it would go to the left, wouldn't it?
What?
If you started it with a yo-yo at rest and then pulled the...
I think it is at rest.
Without, I mean, it looks like you're giving like
It's at rest. Okay, it's at rest. You pull on it to the right.
Freaking out right now.
It goes to the right.
It's lies.
It lies.
Motor.
Magnet.
Special yo-yo.
It's not real. They prove it.
Oh, I only brought one yo-yo. It worked for every single yo-yo.
Crazy.
So what you're thinking is if we pull on it really hard, then this is going to spin and it's going to want to unwind. But actually when the string is at the bottom, this is the trick you can use to wind up your yo-yos. Right? When you put the string at the bottom, you just wind up your yo-yo like that.
It goes left.
Yeah. No, it goes right.
You pull on it to the right, it goes to the right.
The very first one.
Yeah, it goes to the right.
I don't know if you should. Every single.